Hi, welcome to week 2 of Professional Machine Learning Engineer Study Group. I'm super happy that everyone's so engaged. Today, Paddy O'Callaghan from Glasgow was supposed to present, but she's stuck in a car. And this is a group that is organized by different people. I'm a backup, so I'm not part of the lineup. My name is Mariana Bokoy. I'm also part of the GDG Cloud Stockholm, together with Sarah and Mustafa. And the other people that are more actively organizing are Rosa, Majid, Patty, and Sarah. They're all awesome, and you will get to meet them soon. As mentioned, the slides have this order. We're going to look at where are we now on our journey, the guide review, sample questions, and then we've had a bit of Q&A, but maybe some other questions show up, and preview and actions for next week. Let's dive in. Where are we? We are on week 2. So that means you've already done a bit of big data, machine learning fundamentals, and how machine learning works in Google, and as well as a hands-on lab. How has it been going so far? Have you managed to complete all of it, or has it been a bit difficult to squeeze it within a week? You can write it in the chat. I guess a lot of people are in that. It's a bit hard to balance. Take the guidelines as guidelines. You will have access beyond these 6 weeks, so you can continue building up. We're gonna try to guide and open up for questions, and you still have the Slack afterwards. But take it at your own pace. If you are not able to finish everything within the week, it's fine as well. And this week is 2 on-demand trainings, not directly a hands-on lab yet. And those are launching into machine learning and TensorFlow on Google Cloud. Today, we're gonna look at machine learning problem framing, how to translate a business challenge into a machine learning use case, how to define the machine learning problem, the success criteria, identify risks to feasibility and the implementation, and envisioning future solution improvements. And as well, look at the solution architecture, how to design something reliable, scalable, highly available, and translate the business challenge into the machine learning use case, and how to use Google Cloud software components to do that, and to define both the machine learning problem and the success criteria, as well as see how to do that in a way that it is compliant and secure. That is a lot. And when you're trying to define a machine learning problem and the journey, you start with defining the use cases, and that is tied together then with data exploration, looking at what data you have. And depending on what data you have, you will likely select an algorithm that best matches that. Because depending on data, on what kind of data you have, then you have different types of algorithms. Also, depending on what kind of use case you have, you end up having different algorithms as well. Like, for example, if you have numbers and you want to predict the next number, maybe it's enough to do a regression. But if you want to do categorization, then you want to use something else. So it's a bit different. So you decide then from the data exploration what algorithm you choose. And from the algorithm, you decide what kind of pipelines and features you need in order to build the model. And then, of course, you build the model. And once you've built the model, you evaluate it against the test data. And then maybe you iterate a couple of things. And because you see the arrow going back to 1. And when you're happy enough with it, you can present the results, plan for deployment. You can then, once you have this plan for a deployment, you want to operationalize it and monitor it. So you don't just drop something out there without looking at it anymore. You have to make sure that it keeps working and it does what you expect it to do. That being said, Vertex AI is one of the ways to do machine learning models. And these are the building blocks. You can see it from the data readiness, feature engineering, training, model surveying, understanding and tuning, edge, model monitoring, and model management. You can see that it has different kind of phases. And then you can see at the beginning, you have data labeling and data sets, feature stores, and training, optimization, you have experiments, and you have a lot of different things that can help you do the circle that you've seen in the previous slide. So how does one frame a machine learning problem? You look at the problem and you try to see, okay, what is being predicted? As I mentioned, if you have a string of numbers, like for example, let's say apartment houses in Stockholm, which is, if you are not aware with apartments in Stockholm, we always complain that they're very expensive, but I guess there are several cities in the world where this is expensive. But anyway, so you want to see, okay, when is the better price that I should buy an apartment at? And then that is a number, right? So you frame like what is being predicted, like for example, the number. What data is needed? Like for example, for apartment prices, you probably want to see historical data to see trends in price rises or falls, stuff like that, and different features that might influence the price of an apartment. Then you look at the problem. How will users access predictions from the model? How will they use the service? How are they doing it today? And then you can see that you also have a data problem. So it's not just the machine learning part that you have to think about, or how the software should work, but also how will you collect the data? Is there some website out there with all the apartment prices that has all the data you need, or do you need to take the data from a website with prices and another data with, for example, weather? Because let's say when it's sunny outside, people don't want to go and buy apartments, so prices are lower. I don't know, this is made up, but there might be other things that you want to join in these the price data that might make sense. So you might want to collect data from different sources. And then what analysis needs to be done? Do things need to be analyzed before? How do you react to the changes in trends? So you really have to think of a bunch of things in order to frame a machine learning problem. And then if you think about it, you don't want to jump into development without a prototype or a baseline, right? You want to iterate a bit. You maybe, let's say, as I mentioned before, you assume that the weather influences the prices of an apartment, right? And then you think, okay, how can I test this, right? And you build a model. You say, okay, is it and you add in the weather data and you try it out and see, is that really correlating? Is that something that helps me predict things? Does that work, or is it just a wrong assumption? And then you refine what are the different things that you need and what is good data for it. So prototypes are good. For example, you're building a model to predict bike rental duration. And the model's mean absolute error is 1,200 or 1.200 seconds. Great. But is that good or bad? What do you think? Write that in the chat. So the answer was, you actually need the context, as Zara says. It depends, right? Because depending on what does good look like or what does bad look like, it could be different. So how do you define good benchmarks? A good benchmark is constant, and you could have a rule of thumb, or you can have mean medium mode or human experts. It is not necessarily determined by the machine learning. For example, comparing to a linear regression model isn't always the best. The idea is that it's sometimes you want to pick something a little simpler to validate what's good or what's not good. And in our training example, what is the average rental duration given to the station name and whether or not is a peak commute hours? How does our model performance compare to this benchmark? Is the question. If you run a data analysis in our training data and then see how our model is able to compare while using this benchmark example. And then we have responsible AI. What does that mean? It's an umbrella term that covers a bunch of different concepts. And the concepts are fairness, explainability, privacy, and security. And today we're going to talk about two of them, the fairness and explainability. And fairness means ensuring the models are fair and equitable for different groups of users. For example, if you don't need a certain facet or a certain feature, then you shouldn't include it into the model. There are all kinds of examples went bad in production for things where people have included different data and it turned out wrong. For example, there was a machine learning agent that was helping people recruit, and they looked at the current candidates that got hired in the company. And according to that data, including gender data, they decided what are the candidates that would do the best. And they realized that there's a strong correlation between being a guy and actually being hired in the company. So a lot of or women started getting rejected by default because it seems like being a man means you get hired. And that's a true story. I'm not going to shame the company. Maybe I should. But there are a lot of stories like this where people have included different data into the model, and the machine would see a strong correlation, even though it's just historically the case, but it had no direct correlation whether people did well or not, according to those elements. So yeah, we need to make sure that we include the data that makes sense. Then the second thing is explainability. So you need to be able to explain how the decision was taken. So if if someone would look at the algorithm that I mentioned earlier, and they would see, oh, the algorithm made a strong correlation between being a guy and being hired here, they would a human would kind of figure out that maybe it's not a good criteria to select people by. But since it was a machine, machines aren't really evil or non-evil. They do exactly what you tell them to do. So if you tell them to do something bad, they will do something bad without really realizing what they were doing. So we need to take accountability and look at what exactly is the data that we give the machines, and how did they come up with the conclusions that they came up with. Yes. So fairness, understanding the reasons behind a model's predictions can help ensure that the models are treating all users fairly. And then explainability, understanding how and why a machine learning model is making predictions, help us be able to do controls like that. And then explainability evokes a variety of related concepts. Where does data come from? Is there a human in the loop to kind of validate that the machine is going in the right direction? Is it auditable? Where does the model come from? Is the model based on another model that is not having the best of practices? Can this be interpreted? Can this be contested? Then once you have a model, who are the stakeholders? You have the model builders and machine learning ops, and they will have different interests. Like, for example, why is my model not performing? How can I improve it? Then you have the end users that wonder, okay, should I trust it? How should I respond to the prediction? Then you have public stakeholders, where you ask, okay, is the model safe and fit for the purpose? Does it comply with regulations? And there's probably more than these three stakeholders, but whenever you create a machine model, you should not just stay in a smaller box where you think, okay, what do you need from the machine model? But also consider what are the questions that other people will ask around the machine model. Does it do what it's supposed to do? Is it easy to use? And is it complying with regulations and ethics and the purpose that you're building it for? Like, for example, my apartment machine model, if it ends up predicting weather rather than the apartment prices, it would be a bad thing. Then it depends also on the data type. As we started, you can have images, and then from images you can deduct something. For example, there's some images out there where you have an image where they ask you, is this a bagel or a dog? Then you have text, that is free text. It's kind of similar difficulty if it's grammatically correct, or if it has emojis or not, or anything. So you just have a blob of text. Or you could have tabular data, where you have a feature name and a feature value. So there are different ways in which a data can come through. You can see in images, you can do different things with the different types. Like, for example, in an image, you can look at the image and decide what are important features in the image and what are not important feature images. In a text, you could create a model that predicts what's the sentiment in the text. Is it a positive text, or is it something that is hateful? In a tabular type of data, you can see, you can work with the values, and you can see the different values against each other. So it's depending on what data type you have, you work differently with it and you have different wishes from it. The fairness lens, a shoe example. You're in charge of collecting all the shoe images for a fashion classification model. Which type of shoes come into mind? Let's just say it was really, really warm and everyone was using slippers, and colder weather shoes were never cataloged and thought about. And therefore, because everyone was using flip-flops and sandals, the machine never got to learn about boots and winter shoes. And that's one way to have a data gap in your data. You only have a subset of the possibilities of shoes that are out there. So we need to look at the data and see if it really covers the different things that exist already, and get more perspectives. And this is where it's nice to have a diverse group to work with this, because then you get more perspectives and maybe people find types of shoes that maybe you wouldn't classify as shoes, but they actually are shoes. Like, for example, shoes that are corrective for people that have different disabilities. And then we have data bias. There's different types of data bias. Bias isn't always bad. Bias by itself is, in a way, a defense mechanism. And we are kind of trained to detect, is this a tiger? Should I run now? Or is this a kitten? Am I going to go, aw, and pet it? You kind of look at what is natural and what will get you harmed. But sometimes bias is not good, and we have to really examine what kind of biases we are adding to the data. Then we have a data distribution bias. People think that there's a problem with the model. Imagine we have a sentiment analysis, and that uses examples from restaurant reviews. And let's say that we come up with all different types of cuisines, foods, and restaurants, and we have a roughly an equal number of reviews for each of these different types of restaurants. So our data is distributed in a good way. But let's say that, for example, the seafood restaurants in our data set, 80% of the reviews are positive for them, but maybe for vegetarian restaurants, only 10% of the reviews are positive. So this is an example of bias in the way that data is represented. So data is balanced, but it is not necessarily balanced by the label in our data set. And this is going to have implications when we train a model and deploy it, because in the example I gave, vegetarian restaurants will have a much lower likelihood of being classified as positive. But then we have also experiment bias. And the experiment bias is the type of bias that is introduced when labeling your data. So data labeling can take a long time, and often people outsource this task to a group of people to label the data. And labeling is often subjective, and the bias can be introduced in that phase. Let's take the sentiment analysis again and say that we are having people labeling our data in the terms of where there's positive and negative sentiments in the data. And so let's take a sentiment like I'm doing fine. Based on our culture, where you are in the world, that sentence might be positive, or something people might believe this is a negative sentiment. So that's just an example of different labels or ambiguous things that could be there. And the distribution bias, basically, it just means that you don't really have good data across all the different aspects of the data. So you have more data for some things and less data for others. Now, let's talk about how bias can affect your machine learning system. You can have bias at different points in time. You can have human bias in collecting data. You can have bias in labeling data. You can have bias during training using chosen metrics and objectives. So if you have a bias, as I said, that I strongly believe that the weather predicts the prices of apartments, then that's my bias, and I add it in. Now the computer believes that the weather affects apartment prices, and soon that becomes science. The computer told me so it must be true, right? But it all started from me having the bias and training the model with that assumption. So in your assumptions, you have biases. Then you have biases when the user data is filtered, ranked, and aggregated. So depending on how you select things, let's just say that I don't think flip-flops are shoes, so I filter them out. Then I add my bias that flip-flops aren't shoes into the data and therefore the model. And then you have bias when users see an effect. So people can interpret a result in different ways. And then you have the user behavior that informs further data collection. For the last one, there's a funny story where people had an app for roads where people could report that there's a road damage with their smartphone, which was great. And a lot of roads got fixed. But then people looking at the predictions realized that there's this part of town where there's absolutely no damages reported. And it turns out that it was because people just didn't have smartphones, so they couldn't use the app. It's not that the roads were magically perfect, it's just that we could look at that and see that that area has high chances of the road being fine, or rather, but then the reality was completely opposite because that was a poor part where people didn't have smartphones. Solving fairness with the what if tool. So what is the what if tool? There is a number of techniques for solving fairness. Here we can see the what if tool. It's an open source tool that is developed by Google, and it works in any model type, and it can be run from a variety of notebook environments. And it's a widget that you can initialize in your Python notebook. It helps you understand how your model is performing and allows you to inspect different points in your model. And another thing that you could do is you can have an integration with explainable AI that would help you. If you look at real data, you can see that the data sets aren't perfectly balanced. And therefore, you want to use things like anomaly detection and multi-class classification, and especially if you're predicting the occurrence of a rare event. So you can look through your data, and because you are aware that there's this different kinds of biases there, you can try to question if you have this and if it's supposed to be there or not. Then you have unfair versus natural occurring bias. We have unfair versus naturally occurring bias. And as mentioned, bias is often, but not always, a bad thing. And you have unfair bias when data doesn't accurately reflect the population who will be using a model. Like, for example, you have a lot of cats and a dog, but you're looking at a generic pet model. And then you have naturally occurring bias, which refers to scenarios where the data is imbalanced and can't be improved through data collection, like, for example, fraudulent cards. Hopefully, people stumble on less fraudulent cards than correct ones, but who knows with the internet. And then you have choosing the right evaluation metrics, and you can see the accuracy, and you can see what are the different of it. When we have this kind of imbalanced data set, we need to make sure that we are looking at the right evaluation metric to understand our model. Let's say that we choose the overall accuracy as our metric, this might not always point to the best picture of your model, especially when we are dealing with imbalanced data. You can work with downsampling, upsampling, weighted classes. So let's go through it. Downsampling is when you have the majority class and the minority class, and then you remove and discard a random sample. And when you do that, you have to keep in mind that how you do that, you really have to remove a random set. And so there are a couple of caveats. You take care of how you do the downsampling. You don't want to lose the important things. And this is probably the simplest, but it might not work if you don't have enough of the minority class examples to begin with. And then you can upsample. That means that you take the data that you have right now, and then you generate a bunch of more data. And it is a bit more complex because you're generating data, so you want to make sure that it makes sense. But you kind of keep the same type of features, so that's how you have the name. And you basically create a synthetic database. And then you have, like, you increase the amount of attention that is there on the minority class.
What is common between area under ROC curve and area under PR curve is that they both look at prediction scores of classification models. What is different, however, is that area under ROC curves looks at a true positive rate and false positive rate, while area under PR curves looks at positive predictive value and true positive rate.
Then we have the sample question. You can see the full question and the explanation on why the right result is the one that is chosen. Do look through the slides and take a moment to read and think for yourself before going to the answer. Then let's cover a bit of next week. What will be there? Next week, we will talk more about feature engineering and machine learning in enterprise. And then there's going to be hands-on lab around machine learning models and explainable AI. To join our Slack group, you go to bit.ly/RDC Slack. And that's a wrap. I hope you've learned something new. I definitely have. And yeah, thank you. Any questions?